Good morning once again and welcome back to our class in Mechanics of Deformable Bodies. And on our previous lesson, we have talked about Poisson's ratio. And now for our second lesson for this week, we will now talk about the shear stress and strain diagram. Sir, nga nagbalik-balik man taog topic ani sir. Because the previous stress strain diagram that we have talked about was normal stress strain diagram. And particularly, we focus on the tensile stress. And more particularly, we talked about the tensile test of a ductile material. And gadong graph nga ako napakita ninyo last week is a graph of the normal tensile stress strain diagram of a ductile material. And take note, probably nakasabot na mo ani on the previous week, that different materials behave differently on a stress strain diagram. Okay, and that one I've showed you last week was just the stress strain diagram of a ductile materials. But for example, you have steel and another kind of steel, imo na i-graph ang ilang stress strain diagram, dili na sila magkatungod, but ang itsura sa ilang graph, they will probably look the same. But dili jud tungod ang ilang kuan. Okay? In this time, we will talk about shear stress strain diagram. So how is shear stress strain diagram conducted? Probably, our aim for this lesson is that we will learn the shear stress and strain diagram. And we will also be familiar with the term modulus of rigidity. We will also learn the relationship of your modulus of elasticity, modulus of rigidity, and your Poisson's ratio. So those three have a relationship with each other. And lastly, we will also learn these materials that will fail due to either creep or fatigue. And we will learn what are failure due to creep and what our failure due to fatigue are. Okay? So, we have a lot of things to learn for this day, and let's do this. As you can remember, if an element daw, if a square element is subjected to pure shear, this element, di ba we have learned the complementary property of shear. Say pasabot adto, that the direction of the shear should be either going towards each other or going away from each other. And once this material is deformed, it will probably look like this. Okay? And this is your gamma over 2 and your gamma over 2. And if you're going to add this 2, you will get your gamma. Okay, diba? As you can remember, this is your theta. And another way to get your gamma di, diba, we learned that your gamma is the difference of your gamma is the difference of your pi over 2 minus your theta, which is, your theta is this one. But we have another kind of solution for us to solve gamma a lot easier without using degrees and converting it into radians. Let's have an example. So I have this block. Okay? I have this block, and this block is subjected to shear. So, ang nahitabo sa block, ning ana siya. And in this case, where is your gamma? Diba, we already knew that this one is your gamma because this one is your theta, right? And in order for you to solve your gamma, in radians dayon siya, is just actually equal to your tangent gamma, degrees. Diba, we all knew that tangent is equal to the opposite over adjacent. And you can see that this one is a right triangle. And to get your gamma and radians di, all you have to do is to use tan gamma in degrees, which is opposite over adjacent. And let's say this is your delta x. Ang kani ha, kana. Ang pag-change ana niya. And this is your siguro L. Ato lang isulti ngayon ana ha, L. Okay. So therefore, tan gamma is opposite over adjacent or delta x over L. And with this equation, you can immediately determine your gamma in radian na. Dayon. Okay? By using this opposite over adjacent nga principle. So, dagdag kaalaman, and probably you can use this later on our exams. So, yeah. Okay. Let's go back. Ni sibagra ko adto kadiyot kay I just want to tell it to you because that was very convenient to solve. Okay? Now, how is your shear stress strain diagram developed? Diba? Before, we have learned that there was a universal testing machine used in order to conduct the normal stress strain diagram of an object, of a specimen. In the case of your shear stress strain diagram, you have a hollow tube. Well, of course, a tube is always hollow. You have a tube, a thin tube. And kani nga tube, instead of sa atong normal stress strain, ato siya gi-applyan og tensile or compression nga force. But in this case, ang kaning atong hollow tube, gi-subject siya into torsion. So, gilubag siya. And sa paglubag nimo sa kanang atong hollow tube, di ba, at a certain point, sige, ato tan-awon dere. Ato tan-awon ang iyang side view sa atong hollow tube. Di ba, initially, ang atong nagkatungod man ni sila. Nagkatungod ni sila. But, once gani nga, imo siya gibutangan og kanang torsion dira, and probably this one is fixed. What will happen to the deformation? Ang imong diri na side probably mo rotate and mo hiwi na siya at a certain angle. Okay? And that is where your shear stress and strain diagram is developed. And we will talk about this one later on sa atong next chapters. Ako lang mo itagaan og kaning overview ani, but this is how your shear stress and strain diagram is created. And ang imong stress dere is the torque that is applied, and manguta na siguro mo unsa pagkuha sa stress gamit ang torque. We will still talk about that one later. Okay? Later on the next chapters. And your shear strain here is kaning atong change of angle. And again, we will dig in with this one on the next few chapters. Okay? And generally, your material, when it is subjected to shear stress, it will behave in your shear stress strain diagram like this one. Okay? Ingani ang itsura sa atong material when it is subjected to shear stress. So we still have this point, and this is your proportional limit. Wala tay elastic limit, wala tay yield stress, but we have here your ultimate stress, ultimate shear stress, and your fracture shear stress. Ana lang. And the same concept in this region here, same concept sa atong stress strain diagram. This one is behaving linearly elastic. And the rest of the region here is now behaving plastically. Ay, sa mukha eh. So once na gani, nilapas na ang atong stress sa atong proportional limit, from here, approaching to your ultimate stress is your strain hardening. Okay? And I guess probably when it reaches here up to here, basin mao na gitawag nga necking, but I'm still not sure. Kay, di ba, when material is subjected to torsion, na siya portion nga magnipis. So, probably, necking yapon na siya nga part until it fractures. Okay? But, this region here is where your material now behaves plastically. And this small triangle here, your material is behaving elastically. And now, as you can notice, we still have this slope. Again, take note that when our material is still behaving in its elastic nga behavior, dapat maka-imagine mo dayon nga straight line ni siya, proportional line ni siya, nga nani siya dayon slope. Dapat ting ana dayon. But now, sa atong normal stress strain diagram, we call this one as modulus of elasticity. But there is atong shear stress strain diagram. We call this one as your modulus of rigidity. Or, other name, shear modulus of elasticity. It can be. Or, ako, mas comfortable nga tawag ani is the modulus of rigidity. And diba sa atong modulus of elasticity, that is your rise over run. That is stress over strain. And still, the same there is sa atong modulus of rigidity, which is your rise over run or your shear stress over shear strain. And please do not interchange your modulus of elasticity and modulus of rigidity, because your modulus of elasticity can only be applied to elastic materials that are subjected to tensile or compressive stress. But your modulus of rigidity can only be applied to elastic materials that are subjected to shear stresses. Ing-ana ang ilang application. They have the same concept but they are different in some other way. Char. So therefore, kani siya is G. And your modulus of rigidity is equal to shear stress over shear strain. Ano lang? Tau over gamma. And take note, your modulus of rigidity has the same unit of your modulus of elasticity. Why? Because your tau is expressed into stress nga unit and your gamma is expressed in radians, which has no unit. Okay? Let's go to how your modulus of elasticity, modulus of rigidity, and your Poisson's ratio are related with each other. Your modulus of elasticity, modulus of rigidity, and Poisson's ratio are related to this equation. G is equal to modulus of elasticity divided by 2 times 1 minus Poisson's ratio. Why is that so? We will just be discussing this one later on our next chapters. Basta, just take note that these three are related to each other with this equation I have here. Okay? Sige, let's have an example. We have a specimen of a titanium alloy that is tested in torsion. And we have its shear stress strain diagram shown. Our goal is to determine the shear modulus of rigidity, which is katong G, The proportional limit, this is very easy. We have to just identify all the points, the ultimate shear stress. And determine now the maximum distance that the top of a block could be displaced horizontally if the material behaves elastically. So, the second question is, unsa kalayon ang sa babaw before siya mo plastic behavior or maximum sa iyang elastic behavior? That is so obvious. And what is the magnitude necessary to cause this displacement? This is kind of easy. Let us solve this one. Let us first draw the figure. Okay. What is required is the modulus of rigidity, the proportional limit, and the ultimate shear stress. And also, we have to determine the maximum distance nga elastic pa atong material. Okay? And what is the shear force nga dapat nimong i-apply ana nga material para mo deform siya gingana? Ang kaning modulus of rigidity, how can you solve this one? You have your graph and all you have to do is to get the slope of that proportional line, then you can get G. Your tau PL, this can be seen in the graph. This is so easy. Your tau U, this can also be seen in your graph. How about your D? Your D is actually the distance from here to here. And kana nga distance, that is the maximum distance nga ang imong material is behaving elastically. So, ato itawag nga brink of elasticity. Ang pasabot ani, gamay na lang jud nga strain, mo plastic na siya. Okay? So, nana siya sa iyang last moment sa iyang pagka-elastic. Kani nga D. And with this one, we can also solve for your V. Using your shear stress equation. Tau is equal to V over A. Sige, ato una kong solve ang G. Modulus of rigidity. Let us just look at the graph. G is equal to the slope of the proportional line. Unsa may given dira nga mga points. Nagihatag dira ang imong proportional limit sa imong stress is 52. 52 KSI divided by, unsa may tungod niya nga strain? 0.008. This is radians. So your answer here is 6,500 KSI. This is your modulus of rigidity. Pagkasayo na ang taon. How about your proportional limit? The shear stress of your proportional limit. Pwede na ito equals dayon kay makita naman sa graph which is 52 KSI. How about your ultimate shear stress? Kitaan sa graph, 73 KSI. Pagkadali, syarog mazero gyapon sa exam. Pwede ra ni piyungan ka jud. Oh? Pwede ra jud ni piyungan, oh? Ang imong tau 73 KSI. Pwede ra jud piyungan. Okay. And D. Ay, kani kay lisod-lisod gamay. Pero sayo na gud gyapon. Diba? We said that your material is on the brink of its elasticity. So probably your stress and your strain here is now on its proportional limit. Ang kaning atong PL. And we knew that your PL has a shear strain of gamma PL has a shear strain of 0.008. Okay? And we can use that one in order for us to solve for this D. Diba? Kaya we knew that, sa man to, gamma is equal to, diba, nakaibaw ta katong previous na to nga pi over 2 minus theta, and maoning atong theta, and maoning atong gamma, diba? Pero, naputay na learn nga bago pa, sa man tong isa, that is your delta x over L. Diba? And which of these two is easier for you to use? Perhaps this one is much easier. Your delta x is just basically your D here. Okay? And your L is just basically the distance from here to here. So we can use that one. We can use this equation. So, D is equal to gamma times L. And this is 0.008 times, what is your L? Your L here is 2 inches. So, the answer of your D is so small, and it has a value of 0.016 inches. This one is much more convenient for you to solve because radian naman siya dayon. Radian naman eh. Pero kani kay mag degrees pa ka and libog. Okay? So you have this D. So kaning D na to inigabot niya sa 0.016, mauna na siya ang iyang brink sa iyang pagka-elastic. And most probably, if kaning atong decay mo 0.017, mo plastic na ang atong material. Gets? Nga na lang iyang pasabot, ana. And kung kaning D is lesser than this one, then obviously that your material still behaves elastically. Okay? Now, how about the last question? What is the shear force that you have applied in this one? Diba kay morning brink sa yung elasticity ang kadong atong proportional limit sa atong shear strain. We also have a corresponding shear stress nga proportional limit. And unsa man to? TPL is equal to 52 KSI. And we knew that your tau is equal to V over A. And this is what we're looking for. And your area is what? Kibaw na mo, ana, okay? Sige na ito balik-balik before. So, your V is equal to tau times A. And that is just basically equal to, so 52 kilopounds per square inch multiplied by the area. Unsa man ang area ani, di ba? Ang atong direction sa shear and ang unsay parallel niya mao nang area. So unsa may area dira? 3 inch times 4 inch. Wa na ko nagbutag unit kay wa na space. So your shear force is equal to 624 kilopounds. And this is your final answer. Once you already knew the concept and once you already knew how to apply these formulas, then even with the most confusing problems, you will be able to solve. Char. Okay? And yung ano lang pag-solve. I hope you understood the concept of your modulus of rigidity. I hope you understood your gamma, your D, your proportional limit, when can it be applied, your elastic behavior, and whatsoever. Because, again, those things are important. Okay, understood? We're not done yet because we still have another thing to talk about. Our third goal for this lesson is that we should be able to know how materials fail due to creep and due to fatigue. What are creep and fatigue? On the first place, imagine you have a material For example, a rubber band. You have this rubber band. Diba, ang kanang rubber band, inig-inat ni mo ana. And then, inigbuhi ni mo ana. Mubalik siya dayon sa iyang original nga shape. Original nga form. But, if I'm going to ask you, if I am going to apply the same force sa anang rubber band, but let's say I will keep it that way for a long period of time, kung ako siya buhion, what will happen? Will it still go back to its original form? No. Mulutay ang atong rubber band. And that is because of your creep. Because creep is basically a failure or a permanent deformation of an object when it is subjected to loads nga makaya unta niya, but that load is applied for a long period of time. Okay? Kay atong materials, even though makaya niya ang kana nga load, but if you are going to apply it for a long time, then there will come a time that that material will fail. Or it will permanently deform. It will behave plastically. Okay? That is your creep. And an important property of materials that are subjected to creep is what you call the creep strength. And it represents the maximum allowable stress that a material can withstand without exceeding an allowable creep strain. Okay? And how can you determine this allowable creep strength of a material? Actually, there is a graph nga gihimo para sa aning mga creep strength sa atong material. Mo ni ang atong graph. This graph is what you call the stress time diagram. In which daghan nga mga material gitest sila at the same time and with a constant temperature. Nganong importante man ang temperature? Because the temperature can affect the creep strength of a material. So, constant daw ilang temperature, but ang naglahi lang kay ang ilang stress nga gi-apply. And you have this time sa imong x-axis and your stress sa imong y-axis. Ang mahitabo daw, kung magtikadugay ang time, magtikanaog ang imong creep strength until it will probably go asymptotically to a certain line. Asymptote na ha, wala na misaka. And kani sila, mo ni ang mga values sa atong yield stress. So, ang yield stress sa atong material, magtikanaog, or creep strength sa atong material, magtikanaog siya through time. Okay? So, magtikanaog ang quality sa atong material through time. Ano yung nahitabo diri? Ang iyang strength ni naog. And that can be shown on your stress time diagram. The other one is what you call the fatigue. And when can that be possible? Kanang fatigue. Fatigue are usually failure diha sa imong mechanical parts. Why? Sa nasa imong mechanical parts. For example, your crankshaft, your connecting rod, your nasa imong piston, okay? Or nasa imong engine. Ano man, unsa may day nahitabuan na. Di ba na moving parts anang ato mga machines? And sa anang ilang constant nga cycle sa pagtuyok-tuyok, there will come a time na mo-fail na atong material. Bisag walay changes of load. Bisag nakaingon ta nga makaya sa atong material kana kind of load. But since those materials are constantly moving, there are some imperfections of your material nga probably nag-crack siya gamay at the start. Then because of the constant moving of your mechanical parts, then those cracks will get bigger and bigger and eventually it will fail. Failure due to repeated cycles of strain. And it may cause to internal breakdown, and ultimately, it will lead to fracture. So, we have this limiting stress na pud sa atong fatigue. And this is what we call the endurance or the fatigue limit. Kanina pud atong fatigue limit can be determined by this graph na pod. Ang kaganiha, niingon ko nga, sa atong creep, natay stress time. Ang dire na pod, natay giingon nga SN diagram. Where your N is your horizontal, and this is the number of cycles. Number of cycles. And your S is just the stress. Imong gi-apply nga cycle. Okay? And still, it will show graphs like this. For our still siguro, nga siya. Asymptote gihapon siya. So, once gani magtikataas na ang atong number of cycles, then still, the strength of our material will degrade. Muubos ang atong fatigue limit. Okay? So, and ang kaning atong mga number of cycles, they are usually expressed in millions. So, millions ni siya. Okay. Ing ana mapag-design sa atong materials, dapat lig-on. So, millions ng cycles kay para dugay ang life sa atong material. Okay, so that is your difference of your creep and fatigue. Understood? So as a summary for our lesson for today, we have first talked about the shear stress and strain diagram. You have learned the modulus of rigidity. You have learned the relationship of your G, your E, and your nu. You also have learned the concept of creep, failure due to creep, and failure due to fatigue. And I hope that all of those things inyo to remember on their concepts and not just by memorizing those things. Understood? So I hope that you have learned a lot for today, and see you again on our next session. So thank you for your time, and see you again next week. Bye.